Thank you very much for the nice and cool introduction, and thank you very much for inviting me. And thank you very much also for shuffling the schedule to host my presentation today. Should have been another day, but I need to fly tomorrow morning. And I already been introduced, and I want to thank my collaborator. First of all, I want to thank the Fritz Haber Institute, the Humboldt Foundation, for giving me this pleasure sabbatical, and the Fritz Haber Institute for hosting me physically. And then I want to say that all the work I will present today is based on collaboration with some experimentalists and some theoreticians. And amongst them, there is J.P. Maria from NC State, Cormac Toher from Duke, Ichiro Takeuchi, University of Maryland, Marco Mojon Nardelli from Texas, Marco Fornari from University of Michigan, Kenneth Vecchio from University of California, San Diego, Jost Vlasak from Harvard, Jan Schurz from Yale, Natalio Mingo from SEA, Jesus Carrete from SEA, Oleksiy Isaev, and Alex Tropsha from University of North Carolina, Chapel Hill. Okay, so today I will talk about the nice, the bad, and the ugly of material science. That is, after you have learned everything about DFT, because this is a DFT where you learn everything about quantum mechanical energy, you discover that you need more. You need what is called entropy. Okay, so. All right, so the problem of entropy is because, I will show you in the next slides, is that we want to find new materials, okay? So I'm a material scientist. I was trained as you as a computational physicist, but then I moved to material science, and with material science, the deliverable, your career, your future is based on finding new material, not on studying materials that have already been found. Okay, so the way to find new materials, since we scan a lot of configuration, is to find the descriptors to with physical content, as much physical content as possible. This opens another kind of worm, right, which is, you remember this movie, The Good, the Bad, and the Ugly, where the good is that we want to change the world. The bad is that you will be the one that are doing the job, and the ugly is that you do not know how to do it. Okay, so I came to Fritz Haber Institute with a gun in the head, and you can see who's who's pointing who, right? And Matthias has always been very generous, and we see if there is an evolution of this dynamics. Okay, okay, let's go back to science. Okay, the problem of the synthesizability, which is it's called mission impossible. Because we want to understand why some materials form and other times some materials do not form. Okay, so why we trust the thermodynamics, we trust kinetics, we give beautiful predictions, and then when you go to the experimentalist tells you, hey, I can't do these things. Okay, so we're going to analyze an example which looks like a kind of dull, but is actually a very important example because it's going to tell you the trick why. The trick of synthesizability, why a system works and not works, okay? So the example I will take is the samarium hexaborite. There's nothing wrong with it, except that the samarium hexaborite is a potential Kondo topological insulator. Since you are a computational physicist, you might be more interested in the Kondo topological insulator. I'm more interested in why it works, okay? So look, let's go to the phase diagrams of samarium boron. Who has seen these things in his life, her life before? Okay, okay. If you, unfortunately, a smaller subset. Okay, two small subsets. Hey, Patrick, how are you doing? So listen, here you have boron, here you have samarium, and this is a concentration, this is temperature, and those are all the phases. You see, one line is one phase, this region is one phase, another phase, and in between the white part is two phase regions, and then here you have some liquid, and then here you have gas, and so on. Okay, look at here. Here you have a region of samarium boron 6, which is between 10 and 15%. Oh, remember that when you do your calculation with a quantum espresso or VASP or Ames, and you have your geometry, you put one atom in one position. So one position contains one atom. This is not nature. Nature is you have 0.9 atoms there. and 0.1 atoms on the other side. What does it mean? It means that you have range of solubilities, you have partial occupation, and even if the position of the atoms is known, you don't really know which atoms there is there. Okay? So you need to consider this when you go into material science. So in this area, you have samarium boron 6, which means that there are some that you still have a geometry of samarium boron 6, but sometimes you have samarium 0.99 and then or samarium 1.1. You understand, right? So there is a range of solubility. Then this is the melting point. You see that is congruent because the maximum is the maximum of the solid is the minimum of the liquid. So this is congruent, okay? And then you have other phases: samarium boron 4, samarium 2 boron 5. These are not that important because we want this. Okay, so my colleagues, and I will tell you what is this line, right? My colleagues, which is Ichiro Takeuchi, University of Maryland, he has the chamber, vacuum chamber. He has two targets, one of samarium, the other is boron. He shoots two lasers. Of course, the samarium target is very expensive, but anyway, he shoots two lasers, one on the samarium, one on the boron. He makes a mess, he makes vapors of this samarium and boron. So you have, in the chamber there is vapors, okay? And then the vapors recombine, okay? Since you can control the power of the laser through, and you can measure the partial pressure of the gases, you pretty much know what is the concentration of the gas. If I have a boron rich or samarium rich, you understand? And then slowly this gas recombines and then grows on a substrate, a phase that is compatible with the concentration of the gas. Okay, so Ichiro comes to me and says, hey Stefano, whichever is the concentration of the gas, if I go from here to here, from the left arrow to the right arrow, I always get samarium boron 6. This is a paradox, because if I were at the concentration samarium boron 4, I should form samarium boron 4. Look the phase diagrams. This is a line compound. Or if I were at this concentration, I should grow these things. So he says, whichever concentration I start from, I always get samarium boron 6. How is possible? Because the phase diagrams is experimental, so this is given and it exists. So we start calculating, and then here it comes quantum mechanics. We calculate the formation energy of all the phases that are fighting. Okay, don't worry about these parabolas. Just stick with the dots. The dots are possible boron, samarium. This is formation energy. The dots are energies, formation energy of potential organization of the atoms. And the thermodynamics tells you that at zero temperature you need to minimize the enthalpy. Okay, so you need to find the envelope of all these dots where you find the minimum in terms of the minimum points or the minimum style lines. This construction is called convex hull. Okay, so you see that samarium boron 6 is here, samarium boron 4 is here, and then the other one is here. Okay, so since the chamber works at low temperature, zero temperature, and you are in the grand canonical because you have plenty of gas, you can recombine at wish, then you should really minimize the free energy, okay? And if you start, sorry, don't worry about, I'll tell you in 2 seconds. So if you start from this concentration, okay, you should go down in your formation energy, hit the blue line, going to this point, and eventually going to samarium boron 4. So if you follow blind thermodynamics, because we are not thinking still yet, and you come from the grand canonical low temperature, you would have a samarium boron 4. But this is not what happens. It does not happen. Okay, well, okay, let me go back. All right, this is now. Okay, sorry. Okay, this is now what happens. You get samarium boron 6. So my idea was, wow, there is something going on with entropy. And remember that it's entropy, it's just S, but what is the real keyword is not entropy, is T times S, which is the heat. So I try to give a descriptors of the amount of heat that a system can absorb. Remember that you have all this gas. Even if it's a low temperature, this gas is very mobile, so it has a lot of translational entropy, because the atoms can be here, can be here, can be here, can be here. So it's completely localized. So there is a lot of TS, even if T is down, S is very big, so there is a lot of delta Q. We try to capture this delta Q in this phases, and I define these lines. What are these lines? You remember when you calculate entropy in the ideal model is x log x. Remember? It's x log x times a constant, where the constant is the temperature and the Boltzmann, right? This temperature is exactly this x. Okay, what is this? So this temperature is the coefficients which you need to put on top of an hypothetical ideal entropy to go through these points. Okay, what these points represents then, these arrows would represent your equi-heat exchange between the reservoir and the systems. Let's see what happens when you go, all right, when you make these things. If you come from an environment of low, it's not entropy, of low heat reservoir, okay, then you will follow the recipe and you will hit this blue tie line and go to samarium boron 4. Okay? But if you come from a reservoir of high heat, because the temperature is high, or because the entropy is high, or because both are high, then you will reach these lines. Okay, the system, which is a chamber, gas, substrate, everything, we try to get rid of this heat, follow this equi-heat, which is the max entropy with respect to concentration, locus, and eventually end up on samarium boron 6. So you see that the position of samarium boron 6, even if it's higher than samarium boron 4, it has a lower curvature. So you see the trick? Okay, if you change the system and you have the blue below the green and this blue above the red, the samarium boron 6, it will not fall. Okay, so now from these things, then I went to the experiment and said this is how it works, and you might try to cheat the system because you can cool down the substrate, or you can heat up the substrate, and if you cool down the substrate or heat up the substrate, you are moving these points with respect to another, and you can really favorite samarium boron 4 or samarium boron 6 with respect to the others. And everything was following our recipes. So what do we learn from this? We learn from this that even if we want to make a phase, okay, and eventually if you wait 1,000 years you will get samarium boron 4. What formed first is the phase that can adapt easier with the characteristic of the reservoir. If your reservoir has a lot of heat and I need to nucleate myself, or amongst each one of the possible phases, the phases that will nucleate first is the phase that is capable of absorbing, is the one that is easier to absorb Q, so it has the lowest latent heat. Okay, so because the heat needs to go somewhere. Okay, so okay, and you see that actually this descriptor, which is kind of very simple, also correlates with first of all correlates with the solubility, and also correlates with the melting point. Okay, with the melting point. With the melting point. We have a program of melting point. So you see how easy it is to find these things. And actually, you can also go to Masalsky, which is the king of these phase diagrams. And you can tell him, hey, Ted, this phase diagram is wrong because those are not line compounds, but actually should have a range of solubility. So you get information out of these calculations. But now we know everything about samarium boron 6, and let's try to make it more complicated. Okay, new materials. Okay, samarium boron 6 was given and explained. Now let's try to understand if we can use these methods to find new materials. Okay, now let's go back to thermodynamics, which everybody studies thermodynamics, but nobody understands thermodynamics because we study too early in our career. Should be studied at the end, but it's okay. Okay, so listen. Now let's see what happens if we take whichever atoms we want. So you take atom A and atom B. B is not boron, it's just a B, right? You go on the periodic table, you choose A and B, whichever you want, and you mix them. Okay, there will be a probability that you form a compound, an energy of the compound. Maybe they don't mix. You don't know, all right? But if you are able, and thanks to our our database, pretty much we calculated all the binaries, okay, you can find, remember the formation energy with respect to composition of all the possible compounds that you find, okay, given A and given B. So what do? You pretty much do a statistical ensemble of all your phase diagrams, two-dimensional phase diagrams, and you get a number. The number is the expected energy of a mixing if you mix A of B. So given a random A, given random B, what is the expected energy? Okay? So you get a number, just a simple number, electron volt per atoms, kilojoules, whatever you want to pick. Okay? Okay? It's an atom. I put 2D because we have two species. Now the problem gets more complicated because we want to do this for the ternaries. As you know, and this is the trick, a ternary is the marriage of three binaries. Ternary is A, B, C. So when you mix A and B, you have all your lines. When you mix B and C, you have all your lines. When you mix A and C, you have all your lines. When you mix A, B, C, remember, to create a ternary compounds, you need to have a lower energy, formation energy than all the possible combination of the binary compounds. So you see, because thermodynamics is a convex theory. Okay? Okay? So think about this as you are digging holes, and to find one of these points, you need to be better than the others. So you see, the capability to get better reduces because you are fighting against a bigger quantity of potential binaries. Okay, anyway, you go on the database, because we have calculated energies for almost 20 years, and you get all the possible ternaries. We have got like 15,000, and you get a number which is pretty much the expected number of mixing enthalpy if you create a ternary. This is just a number. Then, of course, you have limited data, but you trust what you have, all right? And you get this for quaternaries and penternaries, blah, 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 okay? And of course, the data becomes more scarce because the system becomes more complicated. But then you see that you have to go from 2 to 3, from n to n plus 1. And that's the trick. And you plot it. This is the plot with respect to the number of species of, look only the blue line, of the enthalpy gain. If I have a binary, okay, I'm here, 0.25, and I create a ternary, I expect a 50, 70, 40 milli-electron volt per atom gain. Okay? If I create a ternary. If I create a quaternary, okay, and I go from 3 to 4, the difference energy is this one, right? So I'm going to have a 25 milli-electron volt gain. You see that the gain in enthalpy by adding species reduces. That's because thermodynamics is convex, right? You always try to dig further and further. However, and that's the trick, at the same time, entropy is peaking over. First, you don't know what this entropy is because we do not know that we don't have the model. But even if you use the Dumb model, which is the ideal model, the one that I use on the samarium hexaboride, which is x log x is 1 over n log 1 over n. You have n species, so everything becomes log n. Okay? So in the ideal model, which tends to overestimate the entropy, you see that the entropy is monotonically increasing. So you say, there is a trick here. The red one is monotonically increasing. The blue one is monotonically decreasing. Eventually, they will have a threshold. It's unclear to me where is exactly this threshold, because remember, this is based on some assumption, and some coarse data. But thanks to Nomad, we're going to have a much better blue line in 5 years, and we're going to discover instead of being 3.8, it's 3.9, whatever. Right? But the idea is that you will eventually have a threshold. What does it mean? It means that when Gibbs tells you that to find the stable phase, you need to minimize the free energy, the Gibbs free energy, which is minimum of H minus Ts. If you are below this threshold, you don't care about entropy. You only minimize H. If you are above this threshold, you don't care about enthalpy, and you only minimize minus Ts. Min minus Ts is max Ls, right? So below this threshold, Enthalpy plays a role. Above this threshold, entropy plays a role. Okay, that's why I told you that now you are the new generation. You will study multi-component systems because you want super duper capabilities. You will face a lot of species, and remember, don't use H to find what forms, use S. Okay, so first. Second, we also learn something else. We also learned that if we keep adding species, eventually entropy is going to take over, and we can get rid of enthalpy. Right? And let's see how we can use this in a few slides. In the past, a similar problem was identified. In fact, this picture does not come with me. This picture comes from the Wolverton group. They tried to replicate the stability of the ICSD entries with respect to the, well, forget about the years, it's not important, with respect to the number of species. Okay, so on the bottom are the systems that they are capable of reproducing stability, and on the top, the systems that have been reported. So you see the blue over the blue is pretty much the same area, so they are able to reproduce all the binaries. The red and the red, you know, that's still okay. So they're able to say, well, that's stable from an enthalpy point of view. And you see that the yellow and the green actually becomes dramatic. The green, for the pentanary, is almost no pentanary experimental results can be explained in terms of energy. So that's because the functional of stability is not the energetic, but is the entropic one. Okay. Something similar was also noticed by these Yang and Zhang, these two Chinese researchers that wrote this beautiful paper in this unknown journal. So sometimes you read Nature that are worthless, and then you read unknown journal that are actually full of good science, and I hope that you will read this paper. Okay, so they try to understand what is the ratio, the balance between the entropic part with respect to the enthalpic part. And they really use a very crude, this is no quantum, absolutely, this is like 5 minutes parameterization. All the data can come in 15 minutes, okay? Right, so this is a Vegar's law melting point of the species. This is really a linear combination. This is ideal mixing, x log x. This is a minima hit of mixing, which is really polynomial of some tables, or lookup tables which you mix. So this omega really comes in 15 minutes work. And this delta is really a mismatch in atomic radii, another 15 minutes work. So people that are super quick can do this picture in half an hour, right? And they go on all the reported metal with metal, and they find 3 areas, okay, where omega is big or where delta is big. If you have a big mismatch in delta, you will have bulk metallic glasses. If you have a big mismatch in entropy, you will get, if you have low mismatch in delta, but high mismatch in the entropy stabilization, you will get what is called the S, which are the solid solutions. Okay, this opens 3 regions. Look carefully. In the center, you have structural order, chemical order. This is the place of density functional theory. When you learn, if you use VASP, okay, or you learn geometry, one atom, this position, the other atom, this position, this is exactly the place where you're studying compounds and intermetallics. If you're studying structural disorder, but chemical order, think about the glass. If you put the magnifier, the composition is always the same. It's just all messed up, like the glass. Silica is silica everywhere, but it's all messed up. That's because, but you have structural disorder and the chemical order. You are in the world of bulk metallic glasses, where you need to adapt DFT to do this, right? And if you're on the other side, you have structural order, where you have like a chessboard, and you are populating with different colors. Then you have chemical disorder, but structural order. Well, and that's your problems, no? Because this is what you learn in this tutorial, right? Hands-on tutorial in DFT. But your life to find better material is going to be here, or is going to be here. Okay, so this is what you learn, and this is where you're going to have your success. Okay, that's why it's the ugly part of the movie. Okay, and let's see if we can reverse it. Okay, anyway, so I give you some example where we succeeded on this and we succeeded on that. okay? And actually brought a very good publications for my students. First example, let's start for the lattice, okay? Okay, all right. Let's go back to Gibbs, okay? So I'm so confident that the enthalpy does not play a role, which the best way to address the problem is to neglect it, okay? So I say that instead of minimizing H, I really maximize S, okay? So I say how? I keep adding species. So now let me go quickly. So I take an ensemble for oxides, okay? Since I know that already high entropy alloys, metals, I say, can I do it for oxides? Okay, so I take an ensemble of binary oxides, so X is the metal, O is the oxygen, without any uniform crystal structures, okay, electronegativity or cation coordinations, okay. I take in each one, if I take in couples, they should not have any extensive solubility, so metal oxide A and metal oxide B should not love each other reasonably, okay? Then I will take a bunch of those, you know, I have other ones, but eventually I took this because, we took this because they were cheap, so you need to do a lot of experiments, okay? And the ansatz is, if entropy plays a role, then I know that if I take few of those, there will be no entropy phase. But if I take a few plus one, eventually there will be an entropy phase. So the trick is, what is the minimum number of species, in this case oxides, to reach this threshold, okay, right? So, and I tell you already the solution. If you take, do you see, you have 5. If you take any 4 of those, they don't mix. If you add any combination of 4, you can leave out zinc, you can leave out nickel, whatever you want to leave out. Any 4 combination of these 5, okay, which is binomial 5 or 4, is not going to mix. When you have 5, they will mix. Okay, so this is what we find. If we mix 5, okay, you see that at a low temperature they have each one has their own fingerprints. This is the 2 theta. Okay, and if you increase the temperature, eventually everything becomes zinc. Everything becomes rock salt. Sorry, confused with zinc blende because I'm writing a paper on zinc blende. Every time I think rock salt, I say zinc blende. Anyway, so they become a rock salt. Okay. Remember that also another property of an entropy transition is that since it's based on temperature, disorder, it's like melting, right? If you go up, you melt, and if you go down, you solidify. And it can reversible, can do it many times you want. And this transition is reversible. If you go up in temperature, you make them. If you go down, you go back to the previous fingerprints, these lines, the black lines. And you go going up and down, up and down, up and down. Remember, it's a solid state transformation, so it's not as quick as melting, but you can go up half an hour, down half an hour, up half an hour, and you always find the same things. Up, rock salt, down, a mass of the natural crystal structure of the oxides. Another thing that tells you if you have an entropy-based transition is that, well, let's change entropy, such as a change composition. The maximum entropy that you have for a 5-species system is 1/5, so 20%. So if I go off stoichiometry, which means that I go off the 20%, then I will increase the melting point. Sorry, the melting point. I will increase the transformation temperature. Okay? Because if the amount of heat is constant, if I decrease S, I need to increase T. And in fact, if you take every one, it's kind of cross validation. If you take every one of these binary oxides and you change its compositions from 20%, you see that you have a neutectoid in the hyperspace in the 5-dimensional phase space. It's phase diagrams, and the minimum transformation point is exactly at 20%, where you have 1/2, 1/5. Okay. If it were symmetric, it would be exactly ideal entropy, which is actually, we are lucky, it's almost close. Okay? Then another thing to do is that first you need to calculate to see if they're really put in random position. So you sit on one of these metals. Okay, you just do you measure with experiments. I don't really know how they do, but the position of the other radial distribution function of the other atoms, and then you see I sit on the missing one, which is I don't remember which it is. Okay, and then you see the position of the other ones, and you see they're pretty much the same. Therefore, the lattice is homogeneously random. And you can also see with a differential scanning calorimetry that if you go from low temperature to high temperature, you do the 2 theta as a function of temperature and you plot it, okay? You see that we are not losing mass, and the transformation is endothermic if you go down, and exothermic if you go down, and endothermic if you go up, okay? So this has the characteristics of really a melting, exactly. This is a melting of 5 components that becomes an homogeneous thing. Okay? So this is a new class of systems which we call high entropy oxides, and it was published in Nature Communication 1.5 years ago. Okay? But now, first of all, were we lucky to get these 5 guys? Okay? Can we extend this to other type of high entropy systems? So we went to the Navy. Okay? And we say, well, we can do, these are oxides. I'm not really an oxide person. I'm a metal and carbide person. So I say, well, maybe we can do carbides that resist to very high temperature. Okay? Because, you know, I'm a thermodynamist for structural properties. Okay? So my idea is that if we make a carbide that resists a very high temperature, then we can make rockets that go up and down many times, and nozzles of rockets that do not deteriorate and can be reused, and higher speed, everything. So the idea to find a new high temperature materials with entropy actually was of interest both for the Navy and for SpaceX, which have a collaborator. Okay? So I said, well, maybe we can do carbides and borides. Okay? Here we need to extend, because the idea of just guessing the entropy is not enough anymore. So, you know how you get an entropy. So don't pay attention to this yet. You know how to get an entropy? You have a model. Can be molecular dynamics or can be Monte Carlo. And then you run this model for a long time, and then you do some statistical analysis. You can use you can wait forever, and then you get the free energy, remove temperature, and you get the entropy. You can wait shorter. You use the Wang-Landau method. This works very well if you do not have any phase transition. Or you can, and if you guess right the shape of the initial distribution of states, you can get really the entropy very quickly. Or you use these new methods like the nested sampling method, and which also allow you to jump between different phases. Okay, this is some technicality, but the bottom line, the entropy is a very difficult quantity to get, because the entropy fundamentally is the distribution of your state. So if you're happy with one calculations, to get entropy you need technically infinite, all right? Or infinite calculation or infinite time. So we really cannot get the entropy unless you're willing to wait forever. Okay, so my idea was like, well, listen, then what is really entropy? Entropy, remember, if you're able to calculate all the possible states, is really the thermodynamic density of states. Here you study electronic density of states, right? Number of states within a delta of energy. If you do phonons, you can calculate the phonon density of states. If you do magnetic excitation, the magnetic density of states. So you have E DOS, P DOS, M DOS. This is the T DOS. This is thermodynamic density of states, the number of states of configuration within a delta of energy. So if your database were infinite, which is not, your T DOS would really be the density of these red dots near the ground states. The blue is the ground states, and the more these dots are packed, the higher is the entropy. So my guess is, well, I don't know what is the entropy, but I know, since I go around the phase space homogeneously, I know where there are more or where are less. And if I hope to be able to sample the phase space homogeneously right in composition and in species, then the density of my red dots needs to be related to the entropy. So I postulate, this is a postulate which is an ansatz, that my entropy is defined as can be defined as proportional to the narrowness of the of the histogram. Okay? And now I have a working plan. Why working plan? I define what is called the entropy forming ability of an n-species systems. So you see the entropy forming ability is, well, put -1 on the other side, is the inverse of the thickness of my thermodynamic density of states at the ground states. Well, and then you say, well, thank you, but what do I know? I know nothing. Why know nothing? Because if I want to do a 5-species systems, trust me, I don't have 5 species calculation. It would take me all the computers of Matthias for the next 2,000 years. Okay, so what do? I have to cut some corners. Okay, I say that if the thermodynamic density of state is not available, I sum the thermodynamic density of states like the Kirchhoff sum. Why? Because if you have a thermodynamic density of states with AB, and then you have a thermodynamic density of states of AC, remember that C can become B, so there is a convolution between the thermodynamic density of state of AB and thermodynamic state of AC, and the FWHM tends to get narrower. So if you do dimensional analysis, you discover that this is the only ansatz, logical ansatz that you can give to the pseudo entropy, this entropy forming ability, which gives you extensivity, blah blah blah, and with respect to the number of states. Okay, so this is pretty much a hopeful ansatz. Okay, now the question is, I'm going to skip these slides on details, right? Okay, actually no, it's okay. All right. Okay, listen 1 second. When I have the ground states here, I need to generate the spectrum, right, of all the possible same composition but mess up structures. Okay, we wrote in the past a paper to how to get these things, and actually you should take note of this citation, because it tells you if you have a lattice how you mess up the lattice with partial occupation, so to keep the same concentration and to generate all the thermodynamically excited states. Okay, there is a lot of technicality, and it's based on the supercell, particular supercell, which are the Hermite type of supercells. Okay, that's everything for these slides, but take note of this. I will send you the PDF. If you are students, read it, because this is the key for half of the analysis. Okay. Anyway, so now, if I want to discover a 5 metal oxides, I start, and I don't have the spectra for the 5 oxides. I start for the spectra of the 2 oxides. So you see, you have a metal, oxygen, metal, oxygen, and they put the FWHM here with respect to just a label. And now I need to sum all these things 1 over, okay? And the one that, you remember, the entropy is the 1 over this FWHM. So if by summing these things, if I want to create a pentanary things, I need to do 4 jumps. I start from 0, 1, 2, 3, and 4. Okay, 4 jumps for a binary gives me a pentanary. Okay, so if I want to create a pentanary, I need to do 4 jumps. And the one that is going to be favorable is the one where the total height is the least. Okay, look, given this, the value of the FWHM, you see that actually we were lucky to pick the systems, because exactly if you do this jump up to here, you get exactly the five oxides that we discovered before by serendipity. But you also understand that instead of going from here to here, you can go with the green and you can use scandium, and actually with scandium it's going to work. In fact, we made them. Oh, too much. Can you hear me? Okay, good. And okay, and with scandium it's going to work. But if you want to inject magnesium and nickel and go up to here, it's not going to work. Okay, so you understand with these jumps which kind of combination is going to work, which kind of combination does not want to work. Then you go to the experimentalist. This is what we found. Remember before, we were lucky, it's the one with the FWHM the smallest. We were able to do this one, but we are not be able to do the second. Okay? Now, let's do with the carbides. Okay? All right? You can play the same with the carbides. Carbides are a little more complicated to calculate, but the idea, because the supercell is bigger, but the idea is exactly the same. So you put all your metal carbides, you have metal, metal, carbon, metal, metal, carbon, and then you say, I test all this one, 1, 2, 3, 4, 5, 6, 7, 8. I test 8 refractory metal plus carbon. Each refractory metal carbide is known to have a high melting point. And they say, if I mix 4, 5, 6, 7, I will eventually find a entropy phase which made of a refractory carbide, which is expected to have high melting point. You do exactly the same trick, okay? You can generate a lot of these lines. These are stupid lines, but if you start from the bottom, you can make a combination of this line. And guess what? Okay, you find some prediction, and you go to the experimentalist, and wow, this carbide is a high entropy carbide. This one was made, this one was made, and the other were not made. So the synthesizability of the carbide, okay, follows exactly our predictions. You can do the same for the borides. We have some prediction, but somebody listened to our talk and made and published before we were able to publish the prediction. I share my prediction on a talk. The guy went very rapidly to do the experiments and said, hey, I discovered borides. No, because I told you on the talk 2 weeks before. Okay. Anyway, so there is no way for me to present the borides, but same ideas works for the borides. Okay. And this terminates the upper part, the left part of the 3 area regions. Okay. And now we'll do the last in the last 5 minutes. Okay. Now, remember this picture, right? Okay, you should put it here, right? Okay, remember this picture? Okay, now we have done this one. Now let's do these things, where we have structural disorder, but chemical order. The space of metallic classes. Okay, okay. Metallic glasses or glasses. What are metallic glasses? Metallic glasses are metals. You mix metals and you cool them very quickly. And instead of forming a crystalline phase, they form an amorphous phase. Well, they are mechanically, they are marvels, right? They are Superman, they are superstars, right? Why? Because they are easy to process, high hardness, corrosion resistance, beautiful corrosion resistance. You know where this corrosion starts? On a surface, on a defect, dislocation. If your system is a glass, it's all defects. Okay, so it's impossible to mess up, to create defects on a system that is all defected. Okay, so it's just defected by construction. So they're very highly corrosion resistant. In fact, they're coating the blades for shaving with metallic glasses just because that's why they don't rust anymore. When we were kids, the blades were rusting after you take 1, 2 showers, then they were already rusted. Now they don't rust anymore. They last until long, right? Okay, and they are high yield strength, so they're mechanical also very, very advantageous. High, easy to process. Remember the picture, beautiful picture of Venice. Next hand-on tutorial should be done in Venice. Okay, so you remember that they blow bottles because they create the glass. It's nor solid nor liquid. Well, it's solid, but it's not a liquid. It's viscous. And then they put the pipe, and then they blow, and they create the bottles. You can do the same with metallic glasses. After they glassify, you increase the temperature until they get red, but not the liquid. So they remain glass, and then slowly blow gas and make these weird shapes. Shapes like completely convex shapes that you cannot do with normal stamping or mold that you do industrially. Okay, so from a mechanic, they are just a marvel. The cons is that they're expensive, they contain, they're dangerous, they contain beryllium and other weird materials. Danger is not a problem for us because for us the pseudopotential of beryllium is as dangerous as pseudopotential of oxygen. For us it's just a file, right? Okay, but they are time-consuming and expensive to develop because they're made the trial and error. We do not know which one form and which one do not form. So the challenge was to see, can I predict something? Can I use these things? And yes, we can. Look at here. Think about again, A-Flow, Materials Project, Nomad, all these databases contain these things. Contains structures that are ordered, big, small, whatever, and there is energy, blah, blah, blah. There is as much information, as much metadata as possible, about order structures while we have these things. So look, and we want to use the same histogram method as before. If I'm able to take these amorphous structures, expand like in a basis, maybe with room high in the future, we'll do a compressive sensing expansion, okay? That's very fancy, but if I'm able to say these things is 20% of this, 30% of this, 5% of this, and 15% of that, okay? If I'm able to expand this as a function of that, and from those, I can get all the histograms, this expanded in this, for this, each of this, then the same expansion is going to give me the spectrum for this. You understand the idea, right? Well, it's easier said than done because I need to find how to expand this with this. But here, our friend Villars comes, it's a very famous metallurgist, very rich. He has a huge house in the Swiss lake out of this. Thanks. You see, you can make money out of theory, right? Okay. He really promoted the atomic environments. What is an atomic environment? It's very simple. It's called local atomic environments. You are the gray atoms. You sit on the gray and you look around. This is the environment. So, but how far you look around, that's the trick. You look around until you have the maximum gap. So you calculate the radial distribution function, well, distribution of atoms, the shells. And then eventually there will be a gap, there are all gaps, there will be a gap that is simply bigger, the biggest. Everything that is before the biggest gap is your atomic environment. Everything that is beyond the biggest gap, forget about. So how many there are? There are a lot of them. There are like thousands. You can generate 1,000 of them, but you know, cubic, octahedron, tetrahedron, you can the usual one that you find, right? But Villars was able to prove, analyzing all the experimental report, that if you pick 15 of them, hey guys, 15, you can actually parameterize almost the totality of crystal structure existing. It's like 97, 98%. So if I make 15 routine codes in C++ or in Fortran that calculate the atomic environments for this, and this, project any structure into atomic environment and gets the coefficients, I'm done for 97, 98% of my nightmares. And this is exactly what we do. Given a big position of the atoms, okay, you split. This is your postcard if you were speaking VASP, and those are the atomic environments. This is the coefficient of the atomic environments that gives the crystal structures. Okay, now you have these coefficients. Okay, atomic environments, just make a usual Hilbert space. You have orthogonality, it needs to be closed, and blah, 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 how to get the coefficients. The usual things. It's all in the supplementary information of these Nature Communications. And once you have these CIs, okay, these CIs are this coefficient, this times this. Well, that gives me this. Therefore, once I have this, the CI is going to give me this. Now I have the spectra, that's why it's called spectra descriptor, with respect to composition, with respect to the species, with respect to the disorder that I can dream. And there are some more math, but that's okay, don't worry. It's all convolution of what I told you, okay? And now I go to check with experiments. Before was entropy forming ability, now it's called glass forming ability, but the idea is the same. Okay, look at here, what we were able to do from ab initio versus what? Combination of ab initio versus experiments. Okay, the green lines are the experimental report of glasses. We are done for binaries because that's where we have the data. And the red one is our glass forming ability. Okay, before this didn't work, nobody knew which system formed the glasses, and even less at which composition they formed the glass. Look at here. The green one is the experimental. Say, hey, at this composition, copper zirconium form a glass, and wow, we almost get it right. Look at here, nickel zirconium, we get the one phase, the other phase. We are not perfect, yes, but not only we tell which systems form which glasses, also the composition. Even a difficult system like copper hafnium, where hafnium it has a lot of spin orbit, we get the beginning of the phase and the end of the phase. Look at here, and look at here. Okay. In fact, this Perim was my postdoc. After this paper, he was a recruiter from a company in England, a metallurgical company in England, to study metallic glasses. Wow, just make a paper and boom, get a job, right? Okay. So listen. Now the question is, okay. So you see how well this descriptor works, and now we are approaching the end of the talk, and I was able to show that the model works. It's based on entropy, and now we go to the database. We have a small database. Now, thanks to Nomad, we're going to have more data. But the question is, how many systems might form metallic glasses? Is this, in other words, is this a common phenomenon? Is this a rare phenomenon? Does it happen often? Does it happen rarely? Okay. So we calculate this glass forming ability, and we compare to copper zirconium. We make a threshold, which is a copper zirconium, and we say that everything that is above is going to form the glasses. Everything is below is not. So what is the guess? How much do you think? What is the, and we run this for all the possible binaries. What do you think is the percentage of binaries that might form metallic glasses? What's your best guess? Runhai, what is your guess? Is like a rare or it's a frequent phenomenon? Okay, you don't know. It's okay. Well, it's a right answer. So what do you think? It's like 1%, 20%, 80%? Who says very few? Raise the hand. Who says often?
The art make, I'm going to say it's pretty rare.
You say pretty rare?
I'm going to say pretty rare.
Okay, pretty rare. Okay. And
About 60%, more or less.
well, okay, so he's in between the two, okay? The two guesses. Well, first we have some prediction. Some were verified, a few were verified, a few not. But actually, on our statistics is around 20%. Remember, it's 17, but it's really crude, maybe 10 or maybe 20. What does it mean? It means that the capability to form metallic glass is actually very frequent. Let's say one system every 5. But the problem is to find the cooling rate, which of course is not part of the model. You know how they make? They go to iso concentration, and they make this V-shape wedges. Okay, so this is one temperature, the other temperature, and bam, they cool it very quickly, and they see that since you have the same delta T, but you have different path, okay, you understand what is the cooling rate, right? You can delta T divided by the path per unit time gives you the cooling rate. So this is how they find the cooling rate. So metallic glasses, the world is full of metallic glasses, is full of amorphous systems. I hope I convince you to stop studying the order system and embrace disorder, okay, and noise and confusion, because that's the future. There are many of them with outstanding properties. And I believe that we go back to the ugly was not that ugly. And we actually, remember the picture? We have inverted. So give me the computers, and I will give you the answer of many problems. Okay, and with these slides, I end, and I'm here for questions. Thank you very much.